Welcome back everyone. In this lecture we will see some applications of Sylow's theorem. First we begin with recalling all three Sylow's theorems. So let us start with the group G. So let G be a group. So it is a finite group. So let us say it has cardinality p power e times m, where this e is the largest possible exponent such that p power e divides the order of G. In particularly p does not divide m. So, GCD of m comma p is 1. So, this is what given information. So, then what we know, so we know that there exists a Sylow p subgroup. So, any group of order p power e is called Sylow p subgroup. So, the very first Sylow's theorem says there exists a subgroup h of G such that the order of h equal to p power e. Okay. So, such subgroup is called Sylow p subgroup of G. Okay. So, first theorem of Sylow's says about the existence of Sylow p subgroup. The second theorem talks about how one can compare given two Sylow p subgroups. Suppose H and K are two Sylow p subgroups, that means the order of H and order of G, both of them are p power e. Order of K, both of them are p power e. So, then we can prove that they are conjugate in G. Okay. That means there exists G in G such that G H G inverse is exactly equal to K. In particularly all Sylow p subgroups, they are all conjugate. Okay. So, the third theorem, so that talks about actually a number of Sylow p subgroups. So, if you denote NP of G by the number of Sylow p subgroups. So, since we are in a finite group, so the number of Sylow p subgroups will be finite. So, we can talk about the number of p Sylow subgroups. So, then if we denote that by NP of G, then this NP of G has some constraint. So, this NP of G first of all must divide this M. Okay, it actually divides the order of G and it is also co-prime with p power e. So, that means it should divide M, and if you take this NP of G, so that must be congruent to 1 modulo p. Okay. So, these two important constraints we have for NP of G. So, in particularly we can use this information about NP of G, okay, to say something about, for example, group of orders, group of small orders. Okay. So, that is what we are going to do now. So, we have these three important theorems by Sylow, okay, which actually guarantees existence of Sylow p subgroups and their conjugacy and how to count the number of Sylow p subgroups. Okay, so let us use it and then try to actually conclude many interesting corollaries. Okay, the very first corollary one can apply it for finite abelian groups. So, then it is clear that any finite abelian group is just a direct product of its Sylow p subgroups. So, that is called primary decomposition theorem. So, this is the corollary, first corollary. So, if G is abelian, okay, again you say it is a finite abelian group and you write the order of G, call it capital N, so which is the product of these primes P1 power alpha 1 etc. PR power alpha 1. So, this is the prime factorization of this number capital N. So, then what one can prove? One can prove that G must be isomorphic to this G of P1 cross etc. cross G of PR. So, what is this G of Pi? So, where G of Pi is nothing but the Sylow Pi subgroup. of G. Okay. So, this is an immediate corollary of Sylow's theorems. So, how one can prove this? First of all, existence says there exists Sylow P subgroup for given any prime divisor P of R of G. So, existence of G of Pi is clear from the first Sylow's theorem. So, now since G is finite abelian group, if you take any two subgroups of this G that has order, let us say Pi power alpha I. So, because they are conjugate, so that says that they must be equal, because the conjugacy will be trivial. So, it must be actually equal. So, that says that G of Pi must be normal subgroup of G. Okay. So, here is the proof. So, if you take G of P, so which is the Sylow P subgroup of G. Okay. So, where P divides, let us say R of G. So, then this must be normal in G as G is abelian, because any subgroup of abelian group is normal. So, it must be normal. So, now if you take the product G of P1 times etcetera G of PR, so that must be a subgroup of G. So, there is no other option. But now if you take these R different subgroups, so then look at the intersection between them. Okay. You take one particular G of Pi and then intersect with all other possible products. Okay. GP1 etcetera, GPI minus 1, GPI plus 1 etcetera, GPR. Okay. You take one particular group and then intersect with the remaining products, then it is easy to see that this is indeed trivial. So, what is the meaning of that? That means there is no common element other than identity between these two groups. Okay. So, how one can see this? Note that what is the order of G of Pi? The order of G of Pi is Pi power this alpha I, and what will be the order of this group? So, this is whatever it is going to be the product of those such groups. For example, by induction you can assume that the order must be the product of the order. Okay. So, whatever it is, so if you take any element from this product, so how it is going to look like? So, let us take some G which is in this product, call it pi. So, then this G can be written as some G1 etcetera, Gi minus 1, Gi plus 1 etcetera, Gr. So, that much we know. So, now if you raise this G power product of all this Pj, j not equal to I power alpha j. So, then you can see that, so this is going to be exactly equal to identity. That means whatever the element G, does not matter, the order of G from this product is going to divide this product Pj alpha j, j not equal to I. But if you take any element from this G of Pi, that should divide Pi power alpha I, because that is the order of that group. So, that means if you take some element G which is in the intersection G of Pi intersection pi, then what happens? The order of G divides Pi power alpha I, and order of G divides this product Pj power alpha j, j not equal to I. So, that means the order of G must divide the GCD between them, which is 1. So, that forces G is identity, because this Pi power alpha I and the rest of the product must be relatively prime, because Pi's are all distinct primes. So, that forces that this G must be identity. That means the intersection between the product of GPJs, j not equal to I, and GPI, they are, the intersection must be trivial. So, that shows that if you take the product of all these groups, okay. So, if you take, so this is something I will leave it to you to check. So, this is not very hard to check. So, you can prove that the product GP1 etcetera GPR, now I am taking all product, then this is naturally isomorphic to G of P1 cross etc. cross G of PR. Okay, in particularly the cardinality of this product GP1 etc. GPR is indeed equal to the product of Pi power alpha. I range from 1 to R, which is exactly the order of G. Okay. So, note that the product GPI, it is a subgroup of G which has exactly the order of G. So, that implies G is equal to this the product GP1 etc. GPR, and which is isomorphic to GP1 cross etc. cross GPR. Okay. So, this you can do it by induction. So, this is just by induction you can prove, because when R equal to 2 case we have already done. So, this actually generalizes for the general R. Okay. So, this proves that G is indeed isomorphic to the direct product of its silo P subgroups, okay, whenever G is finite abelian group. So, indeed one can use this information in order to prove the structure theorem of finite abelian groups, which says that any finite abelian group is actually direct product of cyclic prime power order groups. Okay. So, which is something we will be proving later. Okay, this is first immediate corollary of Sylow's theorems. Okay. So, that actually says some very important fact about finite abelian groups. If you take any finite abelian group, it is actually direct product of its Sylow P subgroups. That is what it says. Okay. So, now let us actually move on and then try to understand other groups of orders, small orders. Okay. So, as an example, let us actually start with one particular example. Let us say the group has order, let us say 15. Okay. So, one can also start with order 6, which we have already actually understood. If you take a group of order 6, we proved already it is either cyclic group or it is actually the symmetric group S3. Okay. But now what we want to look at, we want to look at this group of order 15. So, which is just the prime factorization is 3 into 5. So, our claim is this group is indeed cyclic. So, it must be isomorphic to Z modulo 15 Z. Okay, let us see why it is the case. So, now let us look at this n 5 of G. Okay, this is the number of Sylow 5 subgroup. Okay, the number of Sylow 5 subgroup of G. So, what are the condition? Let us call it n5. So, n5 divides 3. So, that means n5 must be either 1 or 3. Those are all the possibilities, and the n5 must be congruent to 1 modulo 5. So, this is the second possibility, but you can see that this n5 equal to 3 will not satisfy this condition, n5 congruent to 1 modulo 5, because 3 is congruent to 3 modulo 5. Okay, that forces that. So, these two condition forces that n5 must be 1. If n5 must be 1, that means the number of Sylow 5 subgroup is 1. But we have already seen if there is only one Sylow P subgroup, then it must be normal, because any two Sylow P subgroup must be conjugate. So, if there is only one Sylow P subgroup, then it must be normal. So, that forces that the Sylow 5 subgroup must be normal in G. Similarly, let us look at n3. So, n3 must divide 5, because 5 is that m. Okay. And then that forces that the n3 has choice 1 or 5. Now, let us take n3, that must be congruent to 1 modulo 3, because the prime is 3. And these two condition, now you can see that 5 must be congruent to 2 modulo 3. So, that forces that n3 must be 1, okay, as before. So, that means Sylow 3 subgroup, that is also normal in G, and let us call this is H5, this is H3. So then you can see that both H3 and H5 both are normal inside G. And what will be the intersection? H3 intersection H5 must be trivial, because one group has order 3, another group has order 5, both are cyclic. If there is X which is there, then order of X must divide 3 as well as 5, because they are relatively prime. So, order of X must be 1, so that forces that the intersection is trivial. So, in this case we know that G must be isomorphic to the direct product of H5 and H3, but H5 is isomorphic to G modulo phi Z because it is cyclic, and then H3 is isomorphic to G modulo 3 Z because again it is cyclic of order 3, but 3 and 5 are relatively prime, that forces that G is isomorphic to Z modulo 15 Z, as 3 and 5 are relatively prime. That means any group of order 15 must be cyclic. That is what it proves. Okay, such conclusions that one can make even for some bigger groups. Okay, bigger groups means some general groups having prime factor exactly two prime factors. Okay, so let's call it as proportion. So this is again corollary of Sylow's theorem. Okay, you can call it corollary or proportion, whatever you want. So let us start with the group G. Let us say it has order PQ and assume that P is less than Q, because we know something about group of order P square. So any group of order P square must be abelian. So and there are actually so one is going to see later using the structure theorem of finite abelian groups. Any group of order P square must be either isomorphic to Z modulo P square or Z modulo P cross Z modulo P. Okay, this is something you can prove even without using the structure theorem. Okay, so maybe I will leave it as exercise. So what is exercise? If order of G is P square, we already proved that G must be abelian. Okay, if G has order P square element, then it must be cyclic. So in this case either this is cyclic Z modulo P square Z, or if there is no element of order P square, then it is Z modulo Pz cross Z modulo Pz. Okay, so you can actually pick one such subgroup and then look at another subgroup, and then you can see that the product of that will be G. Okay, this is something you can verify directly using elementary properties of the finite abelian groups. Okay, now what happens if you have two factors? Assume that P less than Q without loss of generality. Now for some technical reason, let us put that P does not divide Q minus 1. Okay. So in this case we claim that G must be isomorphic to Z modulo PQZ. So that indeed it is cyclic group. Okay. So why this technical condition is needed? Let us see. So let us look at NP. So which is the number of Sylow P subgroups. So then this must be congruent to 1 modulo P, and NP must divide that relatively prime number which is Q. So this forces that NP either 1 or Q. So now you see that NP cannot be Q, because Q, if NP is Q, then Q is congruent to 1 modulo P, but we have assumed that P does not divide Q minus 1. So this forces that NP must be 1. Okay. So that means if you call it HP, so that is the Sylow P subgroup of G. So then you can see that this must be normal in G. So that is what we could conclude. So now let us look at what happens to NQ. So NQ again should divide P. So NQ, the only possibility is 1 or Q, sorry 1 or P. So now NQ must be congruent to 1 modulo Q. So, that forces that this NQ is 1, or if it is P, then what happens, then P is congruent to 1 modulo Q. Okay. But P is not congruent to 1 modulo Q, as P is less than Q. If P is congruent to 1 modulo Q, then that forces that P minus 1 will be greater than or equal to Q. So, that forces that P is greater than or equal to Q. So, that is not the case, P is less than Q. So, that means the only possibility is NQ is 1. So, now NQ is 1. So, that means if you take this HQ, which is again silo Q subgroup of G, so that is also normal in G. So, now we are in the previous setting. Then if you look at G, which has to be the product of HP and HQ, and then note that HP intersection HQ must be trivial, because any element of this intersection should have order that dividing both P and Q, but P and Q are relatively prime. So, it must be identity. So, in this case you can see that G is naturally isomorphic to HP cross HQ, which is Z modulo PZ cross Z modulo QZ. But since P and Q are relatively prime, so this is isomorphic to Z modulo PQZ. So, this proves that in this particular setting, when you have distinct prime factors, when P does not divide Q minus 1 and P is less than Q, then we have G is isomorphic to the cyclic group Z modulo PQZ. Again, the other case also actually can be said something. Okay. So, let us actually look at the other case. So, when P divides Q minus 1, so assume that order of G is PQ and then P less than Q. So, now you can assume that P divides Q minus 1, and then in this case what we can say, of course, G can be abelian. So, G so in that case you can prove that G must be a cyclic group of order PQ. Okay. Because maybe this is something you can check independently. So, the exercise, if G is abelian and order of G is PQ, P less than Q, so then G is isomorphic to Z modulo PQZ. So, why that is the case? So, you have two elements of G, one has order P, another one has order Q. Since G is abelian, so both the subgroups that you generate using those elements, they will be normal in G, and G will be just a direct product of those two subgroups. And since the cardinality of those two groups, subgroups of are relatively prime, so G must be isomorphic to that Z modulo PQZ. Okay. So, the similar reasoning that we told here in this case works here when you assume G is abelian. But if G is not abelian, then what we can say? So, we can assume that G is not abelian. So, then look at this NQ as before. So, this NQ should divide P, that force that NQ is either 1 or P. So, these are all the two possibilities, and NQ must be again congruent to modulo P, modulo Q. So, that means NQ cannot be P, because then P is not congruent to 1 modulo Q, as P is less than Q. So, it is very similar reasoning that we gave earlier. So, that shows that this NQ forced to be 1. So, that means if you take this HQ, this is the silo Q subgroup of G, then it is unique and it is normal in G. So, we can guarantee for sure there exists one normal subgroup of G. Okay. So, now you can see that if you take by using Cauchy's theorem, there is actually at least one element of order P inside G. Let us call it HP, which is generated by x where order of x equal to p. Again this HQ you call it generated by y where order of y is q. Then it is easy to see G is indeed generated by x and y, and in particularly the product HP HQ is going to be G. So, note that HQ is normal, okay, HQ is being normal. So, that implies HP HQ, the product is exactly same as HQ HP. In particularly HP HQ is a subgroup of G. So, that just follows from HQ being normal. Okay. Now, if you take the intersection, so from the previous argument you can see that again this intersection must be trivial, because if we have an element in this intersection, the order of that element should divide both the P and Q, that forces that order must be 1. So, that means the intersection of these two subgroups must be trivial. So, we are in the situation that G is product of this HP HQ, and if you take the intersection between these two subgroups, that is trivial. And note that this HP is a subgroup of G and this HQ is a normal subgroup of G. So, somewhat we are almost in the direct product situation, but except that one group is normal, another group is not normal. Okay. So, this group is not normal, this group is normal, but all other properties are satisfied. Okay. So, such a situation we call actually G is a semi direct product of these two groups. Okay. So, indeed we say in this case G is internal or inner semi direct product of this HP and HQ, and we denote this by HP, this simple HQ, HP semi direct product HQ. So, this direction should be pointed towards the normal subgroup. So, this should be pointed towards the normal subgroup. So, that is the notation. Okay. So, we also want to record which one is normal and which one is not normal. So, this V shape should be pointed towards the normal subgroup. Okay. This indeed actually motivates one to define semi direct product. So, I am actually hiding lots of details here. Okay. The semi direct product is not only depending upon two subgroups, it also actually depends upon how one of the subgroup is acting on the another subgroup via these conjugations. Okay. So, maybe in the next class I will explain all those details, but what is this actually analysis says. So, again once you know what is semi direct product, then basically using Sylow's theorems, so you are able to determine all possible groups of order PQ. Okay, for distinct primes P and Q. So, when P does not divide Q minus 1, you are getting a cyclic group of order PQ, and when P divides Q minus 1, there are two possibilities. So, when it is abelian, then you are getting cyclic group of order PQ, and when it is not abelian, then you are indeed getting semi direct product of those two cyclic groups. So, that is you see that HP is nothing but Z modulo PZ and HQ is nothing but Z modulo QZ. So, basically you are getting semi direct product of these two groups as your G. And of course, the semi direct product depending upon how this group actually H acts on this normal subgroup via conjugation. So, if you actually change the action, then you are expected to get various different semi direct products. Okay. But in this case, when you look at these two particular examples where Z modulo PZ and Z modulo QZ such that P divides Q minus 1. So, then you can prove that it does not matter how this Z mod PZ acts on Z mod QZ, all the semi direct products will be isomorphic, and that isomorphic group That's what you get when for this order, particular order PQ. So there is only one non-abelian group of order PQ, so which is exactly given by this unique semi-direct product of Z modulo Pz and Z modulo Qz. So this is also called, so the G is also called extension of this Z modulo Pz by this Z modulo Qz. So basically we are saying that there is only one extension possible in for this particular groups. Okay, I will explain in the next class what is the semi-direct product, and then how to define both the inner semi-direct product as well as outer semi-direct product. Okay, using that we will actually see that. So I will not be able to prove that if you take all possible semi-direct products using this two groups Z modulo Pz and Z modulo Qz, you will be getting same isomorphic non-abelian groups. But anyway, so I will just define it and then leave it to you to think about it. Okay. So I will stop now. Like I said, we will continue with the semi-direct product and other possible applications of Sylow's theorems. So we will stop here now. Thanks.